This is about mixed fertilizer formulation. And normally these NPK fertilizers are simply prepared by mixing the nitrogen fertilizer, phosphorus fertilizers, and potassium fertilizers. So we have this nitrogen, phosphorus and potassium. Potassium is K, no? Here, a mixed fertilizer having NPK composition of 10:26:26. 10, 26, 26, which is 10%. 10 percent. First number corresponds to percentage nitrogen, second number corresponds to percentage P2O5, and the third number corresponds to percentage K2O. Okay, there is already also mentioned, but NPK, this representation is first number is N and another is next is a P in terms of P2O5 and K in terms of K2O. So these are all these numbers in terms of weight percentage. Otherwise, given taking if you see these numbers, they say like in the fertilizer of 100 kg, you have 10% of nitrogen, 26% P2O5, and 26% K2O. There is a way we should understand. Maybe the relevant idea you can take it from this about the chemical. In the chemical technology book, they used to say this in much detail. Otherwise, this is 10%. 10% this fractional N atomic nitrogen, and 26% as P2O5, and this is 26% as K2O. Okay, it used to be formulated by mixing ammonia, phosphoric acid, potassium chloride, and sometimes they also add urea in place of this ammonia. Okay. If anhydrous ammonia, anhydrous phosphoric acid, and 100% potassium chloride are used for mixing, calculate the amount of each of them required for formulating 100 kg of the mixed fertilizer. Assume that the filler will make up the rest. So otherwise, you can see. You ask, no. So what is this? This will not result lead to. For making this 100 kg, you will calculate this required amounts, and if there is a if these three components are not adding to 100 kg, they will add filler, but the filler doesn't contribute for any of these NPK, no? Because they are they don't have any fertilizer value. Okay, there is a meaning of this. We'll try to understand that. Okay, first we'll finish that and come to the second part and third part. So what is needed is we need to prepare a mixed fertilizer of 10:26:26, which is percentage nitrogen, percentage P2O5, and percentage K2O. These are all in weight percentage. So it is obtained by mixing anhydrous ammonia and anhydrous phosphoric acid and pure KCl. So always N1, N2, N3 are to be obtained. Since we have data, we can make this. Of course, there is a statement, no, for 100 kg of mixed fertilizer. This N4 is available. N4 in terms of mass is available. Now, here normally you are mixing only KCl, but you are reporting the product is to have K2O. Which means KCl to K2O, how it will happen because of some oxidation reactions. Then only you can convert that to K2O. Always from KCl, how to get K2O. There is involving a chemical part, but we are not going to use that any stoichiometry or anything. We can directly make use of our atomic balance approach, which is very convenient because how many atoms are there? HNPO. As well as of course I'm not using atomic balance. I'm going to use. Okay, so we can write as balance on K, P, and N directly, simply, because only these three are appearing in this product. Of course, we don't know about this Cl content of the product or what is it, H content of the product. So though there are many 1, 2, 3, 4, 5, 6, 7. There are 7 atoms involved. but the product is having only this data about N, P, out of 7. I will write that, no? 7 atoms entering. For 7 atoms, we will be having data. If you know this N1, N2, N3, product we have N, P, O. That means only 3, 4, 5. Only 5 atoms are. Only for 5 atoms we have the details in the product. So which means we can only write 5 atomic balances. But is that required or not? How many balances are this? What are all the things needed? We need to get this N1, N2, and N3 because these are all pure components. And we are having the mass of N4. How much of mass to be prepared that is available for preparing 100 kg of mixed fertilizer. So we can simply write these balances on N, P, and K. Or simply you can write the atomic balance, how much of N entering with N1 and how much of P entering with N2 and how much of K entering with N3. There is this K entering here is the K leaving and P entering is the P leaving here and N entering here is the N leaving. So the atomic balance are quite straightforward. So, but here the informations are in terms of mass percentage, mass percentage. So we need to have this masses in terms of moles. So otherwise, we know the data of these atomic weights. These are all taken from the table, and we need to know the this molecular weight of these components as well as P2O5 and K2O. So for every component, I am writing this in terms of writing the molecular weight. Because what is the need for molecular weight? Because this atom balance, we will be writing the mole numbers multiplied by the this stoichiometry. What is it? Say for example, if you write the atom balance for this, say this NH3 is having 3 atoms. There is 1 mole of NH3 will have 3 atoms. Whereas this is only in terms of moles and atoms are only from moles you can write the atom balance. So that's why these molecular weight data are used. We are given with the data like for 100 kg of mixed fertilizer, product is to have 10% N2O, what is it, 10% N, which is 10 weight percent, no? And P2O5 as 26% and K2O as 26%. There is a meaning of this, no? 10%, 26%, 26%. These are all by weight. So there is 10%, there is 10 kg. Out of 100 kg, we have 10 kg. The product will have 10 kg of nitrogen and 26 kg of P2O5 and another 26 kg of K2O because of 10 is to 26 is to 26. So I'm for this mass of fertilizer, we need to have these masses in of nitrogen and P2O5 and K2O. So this mass in terms of kg, I'm converting into mole. So divide by molecular weight. So these are all the moles of nitrogen. This is that we in the product. And this nitrogens are simply coming from this only nitrogen is coming from only this stream N1 and this P is only coming from this stream 2 and K is coming from stream 3 alone. So now you can write atomic balance on this nitrogen, which is how much moles is entering this based on the basis of 100 kg of mixed fertilizer. We know the product is having 714.3 moles. So product this 714.3 mole is coming only from this N1. So this 714.3 is already simply N. So and how much of N is there in N1? Only 1 N is there. Or is this NH3 is having 1 gram atom of nitrogen. So by making atomic balance, so this 7 or is this nitrogen in the product is nitrogen of the ammonia. So 714.3 is equal to simply N1. So from which we got this ammonia, how much of moles is entering, that is N is directly available because of the N of the product, nitrogen of the product. Okay. So from which this is available in terms of mole multiplied by molecular weight, you'll be getting in terms of gram. That divided by 1000, you'll be getting in terms of kg. Likewise, you can make the atomic balance on P. So P of product, which is 183.1 multiplied by 2. Now the atoms of P, this is mole, and multiplied by this stoichiometric coefficient, you'll be getting so much gram atoms of P, what is it, P. So 183.1 into 2, it is what is this, what is it, P2O5, there is 183.1 multiplied by 2. There is a P leaving, and the P entering is simply N2. Otherwise, N2 is equal to P2, P entering is only in N2. This N2 is having only one P. This N4, in the N4, we have 183.1 mole of P2O5. 1 mole of P2O5 is having 2 gram atom. So that's why we have this 183.1 times 2, that is equal to N2. Okay. So this is based on atomic balance on P, or is phosphorus. So from which we get the phosphoric acid amount in terms of kg. So ammonia amount is available, phosphoric amount is available. The next one is potassium chloride. So potassium chloride, or is we can write this equation now. So the product 276 moles is having 276 into 2 gram atoms of K. That is simply coming from the N3. Otherwise, this N3 is also having 1 gram atom. Otherwise, N3 moles is having 1 gram atom. So here product is having 276 into 2. That is equal to simply N3. N3 is 552 mole. Then what is here? This is in, of course, we need to convert that to kg. So this is the molecular weight of KCl. So otherwise, why we have used these atomic balances? The reason is here it is in KCl, here it is in K2O. Otherwise, to have one K2O, definitely you would have used 2 KCl. Otherwise, if you want to get this 1 K2O, we need to have 2 KCl making some reaction. No? Otherwise, KCl plus O2 giving rise to some sort of reaction KCl. Sorry, what is it? K2O. You should get K2O. So in that case, of course, I haven't written the fully balanced equation. For getting K2O, of course, this is to be written as 1 by 2. Maybe you can also still write now. So this will be the formation of this K2O from this KCl. We have this feed KCl. Product is reported in terms of K2O. Of course, there is no such reaction happening, but though by having KCl, you can also get K2O. KCl plus this oxidation is going to this 2K, or is K2 into O and Cl2, or is this a reaction possible? No? So this 1 K2O is coming from 2 KCl. That is also understandable here. So here, how do you write the balance on K? Balance on K is N3. N3 refers to the KCl entering. 1 KCl is having 1 K. So that is simply N3. And here the product 1 K2O is having 2 gram atoms. So 276 gram mole is having 276 into 2 gram atoms of K. There is a K leaving. Okay, this is a K entering. So now we can we have reported everything. We have calculated every fertilizer constituent in terms of kg. Now the second part, there is a second part. Instead of 100%, instead of anhydrous ammonia, which means pure ammonia, we are using 100% pure urea. In place of ammonia, if urea is used, how much will be the urea requirement? In that case, what it will be changing? Ammonia is giving for this N contribution of N. You can also get that from urea. So what is a molecular formula of urea? This is simply NH2CO. NH2 is a molecular formula of urea. say here we should not do much calculation because already we know this N1 requirement. So is urea, which is having a molecular weight of 60, that you can check it. And we need this 714.3 moles of nitrogen in the product. This is already found using the available mass percentage data, or using the mass ratio data. And for a mixture of 100 kg of mixed fertilizer, we obtained these to be the amounts of these. So for getting this 714.3, we need to calculate how much of urea to enter. So for 714.3, of course, one urea is having 2 nitrogen. So this nitrogen, product nitrogen is 714.3 mole, and feed is always 1 mole of feed will be having 2 nitrogen. N1 mole of feed will be 2 into N1. There is a gram mole of gram atoms of N entering. N1 into 2. This is the N1 is the moles of urea. Okay. And so this is already available in the product, and this is N1. We are going to find one N1 is having 2 moles of nitrogen, 2 gram moles of 2 gram atoms of nitrogen. So when we say like atom, it is gram atom. Otherwise, when you say like molecule, it is gram mole. Okay, now we are getting this N1, which is in terms of moles, and how to get this in terms of kg. So this is moles. N1 is moles. N1 is in urea, right? N1 is urea. And what is the molecular weight of urea? 60. So is this multiplied by 60, will be getting, this is roughly about 4. Yeah, I will be getting this. This will be, if you multiply this and this, you'll be getting in terms of moles into molecular weight, you'll be getting in terms of gram. Divide that by 1000, you'll be getting in terms of kg. Okay, otherwise, for the second part of the question, in place of ammonia, urea in place of ammonia, simply work for the urea and ammonia part alone. No need to calculate the other parts. Since we know the nitrogen of the product, so that is coming from the nitrogen of the urea. So this 714.3 is simply 2 into N1, because one N1 is having 2 En atomic nitrogens. Okay. So this part is okay. There is also another part, but I am not going to discuss now. You can go through that part. Okay. I will send you, this material will be also available for you to go through, which is in place of, instead of pure urea, in place of pure anhydrous ammonia, of course, we have still anhydrous ammonia. In place of pure potassium chloride, we have 98% potassium chloride, which means there is a inert of 2% available. There is non-fertilizer content is there in the potassium chloride fertilizer. And the this phosphoric acid also not 100% phosphoric acid. And earlier we were having anhydrous phosphoric acid. Now the availability is only phosphoric acid of some lesser strength, that is not 100%. So you are asked to find how much of what is the strength of phosphoric acid required for making the mixed fertilizer of 100 kg. Or is this statement 100 kg is still applicable? In place of this anhydrous phosphoric acid, we are using a phosphoric acid of reduced strength. And in place of 100% potassium chloride, we are using 98% potassium chloride feed. So maybe we will also complete that here. What is this is aqueous phosphoric acid is entering, which is having has 3 PO4, the fraction of which is X, and the balance is water, or is 1 minus X is the water content. And feed ammonia, we were already taking it to be 12.14 kg of anhydrous ammonia. Still, we are going to use the same anhydrous ammonia. Or is this part, there is no change. Here, there is a change, as well as here, there is a change. So what is the change? Earlier, we were having 100% KCl. Now we have the KCl fertilizer is only having 98% KCl. The balance is a non-fertilizer content. And the product, we already know this based on the molds. These molds are coming from, these molds are supposed to come from the pure component. Yeah, here, no? These molds are coming from, this N is coming from this 714.3 ammonia, and this P2O5 coming from this part. So always we know the values of N1, N2, and N3, which are all in terms of moles. I am converting that to mass. Already we have did that part. So how much of pure this NH3, and how much of pure H2 is H3PO4, and how much of pure KCl required. So these are all only written here. So is your product, this product is going to have these contents. These three is not adding to 100 because we want to have a 100 kg. So of course, the KCl fertilizer, whatever we used, is only 98% KCl. The balance 2% is simply a non-fertilizer content. So this is the non-fertilizer content is 0.02 into M3. So how much of water is available? Why it is coming? Because of this we are using H3PO4 of reduced strength. So whatever the this is going to fill up the balance. In what way? Why we are simply going to mix this anhydrous ammonia and 98% potassium chloride and phosphoric acid of some strength to make the required fertilizer. So here we don't have any filler. Earlier there was a statement about filler will make up. Here there is no filler. Or is only the water will make. Or is only this feed only is resulting to, feed itself is resulting to 100 kg. So this ammonia content, whatever already we calculated, is the same. And for here we already have only 100% potassium chloride, but we are only now using 98% potassium chloride, which means the 2% inert will be such available in the whatever is entering in the KCl fertilizer will leave. Is here 71.15 kg that we are entering. Now instead of 41.15, instead of 41, there is the product still will have 41.15. How it is? Yeah, there is this 41.15. We were having originally pure KCl. Now we are having 98% KCl. So in that case, we need to have the product should have this amount. Then only the K part will be met with. So otherwise, this product is still having 41.5 kg, 41.15 kg of KCl. The product amount will be now altered because this 98% is adding to 41.15 kg. So from that you can get M3. This 98% of M3 is 41.15. Now why it is 41.15? Only from 41.15 we'll be getting the required K part of the mixed fertilizer. And this is to be 35.89, which is simply the pure H3PO4. But here we can have impure, or what is it, aqueous H3PO4, because after this component there is some balanced water. So how to get the balanced water, which is all these three, this 100 minus of all these is the balanced water. So 100 minus this is 10.82, and this is already minus that. Okay, there is this hydrogen balance, water balance we can make. Now this KCl we can easily calculate, because 41.15 divided by 0.98 will give you how much of this KCl fertilizer to enter. Okay, that is over. And balance on water. So water is entering in this M2 into 1 minus x. M2 into 1 minus x is the water entering. And water leaving, already we made that, which is 10.82 and that other part, no, because this is the total other components. 100 minus of these will be 100 minus of these will be simply water content. Okay. So from that we could get a balance on water is resulting with one equation, and balance on H3PO4 is directly giving a equation. What is balance on H3PO4? M2 into X is going to be H3PO4. Okay. So using that we could get X. What is needed is X. X is the fraction of mass fraction of H3PO4 in the solution. Otherwise, there is a strength of the phosphoric acid solution. Of course, the calculation is lengthy, appearing to be, but simple only. I will tell you again this problem. This is about formulating a NPK using this ammonia, phosphoric acid, potassium chloride. Sometimes they are available as a pure form, or it is in acid of reduced strength, and potassium chloride again having some non fertilizer content. Okay. Here the first part is about anhydrous ammonia, phosphoric acid, and 100% KCl are mixed for getting 100 kg of fertilizer. Of course, these three components, if you simply mix in this proportion, it is not leading to 100%. The balance, there will be some sort of filler to make up the 100 kg. Okay, there is a meaning of this statement. And the second thing is, in place of ammonia, we are using urea. Because of that, how much is the urea requirement? Then the third part is about we are still using the anhydrous ammonia, and in place of 100% potassium chloride, we are having 98% potassium chloride. The balance 2%, there is no information, which means it is not water. Potassium chloride is some sort of component. There is the balance 2% we can treat to be a non-fertilizer content. Here, the strength of the phosphoric acid, which means normally phosphoric acid is 100%, or what is it, aqueous phosphoric acids are available. Normally, these inorganic acids are available in terms of aqueous solutions. So whereas KCl component as like NaCl, which need not have this water, or is this 98%, the balance 2%, I am getting it. There could be a non-fertilizer constraint. Okay, that's why this third part we had here. Is I don't treat this 2% as water. I simply treat that as some inert, which is 2% of M3. So from that I'm getting the equation for water of the product. Water of the product in terms of M3 is available. Then we could solve for the rest of the part. Okay, nice learning on these three problems. One is about simply mixer acid formulation. Another thing is about evaporator problem with salt crystallization. The third one is which is about mixed fertilizer formulation. So these three problems are, of course, only for this part we need to have this mole balance approach, or what is it, atomic balance we have used. The reason is the product and the feed are of different chemicals. There is only this P2O5 is not readily available in the feed, which is available as H3PO4, and K2O is also not readily available in the feed, which is available as KCl. So since they are I think the atomic balance is very convenient. So whatever the atoms of this P2 has to definitely come from phosphoric acid, H3PO4. And what this K2 of the product should have to come from KCl. So this atom balance is very convenient to make this fertilizer color formulation. Whereas for evaporator, we were working only in terms of mass balance, which is very convenient. And for mixer acid formulation also, we are using only mass balance, because the acid in the feed is remaining as the acid in the product. Here in this fertilizer, we see we show the product as different composition, whereas the feed is of different contents. That's why, so whenever you see any chemical transformation, better to go for this moles. There is an idea we are getting from this problem.